The only difference between the conservation of energy problems we did first semester and now is that we need to track the motion of the center of mass. You're answering questions that are not the question being asked, which is why I said to everybody who wrote down that the kinetic energy was 1/2 I omega squared, did I ever ask how fast it was going? And do you have any information about how fast it's going? I mean, that's not the question. I do know that there is this intermediate point in the problem where the object will reach this point. Don't you agree? It's at this moment that there will be a collision between the bar and the box. And it's at that moment where the bar is going to lose energy because it's in the middle of a collision. However, the speed that it has just before the collision is based on mgh, right? Now, after the collision, it will be traveling faster or slower than before the collision? Slower. How do we know? Doesn't swing up as high. We don't know how fast it's going after the collision, but we do know how high it swings after the collision, which means after the collision, the amount of energy it has is mgh final. I never once needed 1/2 I omega squared, not once. I may in the future when we actually analyze the collision portion of this, but we're not there yet because we keep dragging our feet about silly stuff like this. And still, I think there's people in the room who don't really recognize that there's an important level that we should probably draw into this problem, right? Doesn't this represent the lowest point of the center of mass? The middle of the bar when it's vertical? That would mean that this will be the height for here. And whatever this is will be the height for here. You were taught how to do this. The difference was that when we did this the first time, it was a big box at the end of a string, and we didn't care about the mass of the string. That's not what we have now. Now we have to deal with the fact that the whole bar has mass. And because the whole bar has mass, we have to deal with it differently. The center of mass of the system becomes important. So on the left side, the amount of energy is just going to be mg L over 2. And you were given a method to figure out the height when given an angle. So you should be aware, this side, mg L over 2 times 1 minus cosine 30 degrees. None of that has changed. And yeah, I think this is going to be greater than that. So this system loses energy. Nothing new here. That's why I'm disappointed. I need you guys to be able to do this. I added one small detail on Tuesday. I asked you to employ it here. Trust me, this problem with the collision in it is different than what we did before. This system is experiencing an external force during the collision because it's fixed in space here. Before, we just had an object that was attached to a string, so it wasn't really experiencing an external force. This object is, because it's physically attached there, while the other one was just tied to a string. That makes this different. This object's linear momentum is not conserved in this collision because it experiences an external force. But angular momentum is different than linear momentum. So we've got to nail all the energy stuff because at least it's more or less the same. We'll see. Maybe that will be enough to jumpstart you for this one. So I have a merry-go-round. It's a disc, 200 kilograms, and has a radius of 2 meters. It's a merry-go-round. Let's say that there's a motor that maintains a constant 6 radians per second. 4 kids step onto the merry-go-round, but the speed of the merry-go-round doesn't change. Each kid stands at the very edge, and the kids have a mass of 60 kilograms. After a few moments, the kids all walk to the center. They make it to a point 1 meter away from the edge. But the motor still continues to spin the merry-go-round at 6 radians per second. How much work was done by the motor? 60 seconds. 2 minutes. How much work was done by the motor? Certain. Again, the problem we did this problem on Tuesday as well. We talked about it. It was in the FRQ from last Friday. So this isn't new. You have a decision to make about how you would calculate work. You can choose to calculate work using the definition of work, which, for the sake of torque, looks something like that. But we don't know anything about the torque applied by the motor. We don't know what's actually the number of rotations or anything it makes while the students are moving from the outside edge to the inside edge. If it's the torque if it's the work done from an unbalanced torque, then we could consider the change in kinetic energy. Is there any reason to believe the kinetic energy of the system changed? Omega didn't change. Did the moment of inertia change? So it did. But you don't have to think of it like that. That's just a way of thinking about it. We have 1/2 I of the disk. Did the disk change? No. Plus 4 times I of the kids. Their point masses, right? mr squared times omega squared. Omega didn't change. The moment of inertia of the disk didn't change. Did R for the kids change? Did it increase or decrease? Decrease. So the moment of inertia of the system became less. Right? But if you if you're having trouble thinking of it like that, the kids have twice the speed at the edge than they do here. Because it's still true that V equals omega times R. Right? They have half the velocity. If you don't want to think about it as rotational, then 1/2 mv squared. Right? Here they're traveling at 12 meters per second. 6 times 2. Here they're traveling at 6 meters per second. And that value is squared. So they have a significant reduction in kinetic energy when they walk from the edge to the middle. They would feel that. As they were walking, they would feel a force against their feet, slowing their horizontal velocity. It would make them stumble in the direction they were going. You should try this. So when you're at the mall or at Busch Gardens, ride the carousel and get off the horse you've been assigned and walk towards the middle. They'll yell at you because you're not allowed to do this. And they'll kick you out of Busch Gardens and they'll kick you out of the mall. So I'm saying on video right now, don't do this because I'm recording. But I am saying that if you happen to have a couple of kids with you and you set the kids on the horses, and if you were like me and you might have 3 kids with you, you can't stand in the middle of 3 kids because there's 3 kids, 3 horses, got it? So you might have to move from between 2 of the horses to between the other 2 horses. That would mean you'd have to walk towards the center, right? It's a physics experiment. Just borrow 3 kids. That way you have a plausible excuse for why you'd have to walk from the outside edge to the inside edge. You're looking out for your kids, right? That probably won't work. And don't go borrowing anybody's kids for this experiment. But what I am trying to say to you guys, with all sincerity, I didn't ask you to do very much here. If you're struggling, that's got to be a little bit on you. This side is going to be less. Negative work was done by the motor. Look, the thing was easier to turn. What you're about to find out is because it was easier to turn, the motor had to actively prevent it from speeding up. You see, we're missing a piece of the puzzle. And I can't keep, I need to move on. But I need you guys to be remembering the old stuff so that when I bring up the new stuff, you still can use the old stuff. You see, the piece of the puzzle that's missing here, and why this is important, is that we need to start talking about momentum. And this is the last piece of the rotational discussion, but it's a big one. It has lots of dynamics to it. I'll remind you a little bit about what momentum was about. You've been paying attention to some of the easier things. Can you translate this into what angular momentum must look like? You've been playing along. Every time we have something about that was mass, what do we use instead when we talk about angular motion? And instead of V, right? This is angular momentum. But it is a vector. The vector is in the direction of the omega. Use the right-hand rule for that. Now, P didn't make a whole lot of sense, but we're just out of letters. So capital L is not going to make much sense either. But that's the symbol that we use for angular momentum. Look, I've been giving you the easy stuff so far. Energy is relatively easy. And energies add together. Momentum is distinctly different. The units for momentum, when we talked about translational momentum, was kilograms, meters per second. Look at the units for angular momentum. I is kilograms meters squared, and omega is radians per second. The units are different. These are different measurements. They express different things about the object. So an object can have linear momentum and not angular momentum, and vice versa. From this point forward, we need to be more careful. That's why the first thing I want to point out clearly is that angular momentum, like linear momentum, is a vector quantity. An object wishes to maintain its state of motion. Momentum is a measurement of that maintenance of its motion. So if an object has linear momentum, it wants to maintain that momentum. The same can be said for angular momentum. Once you set something spinning, it wants to stay spinning. But direction is critical to understanding momentum. It's a vector quantity. So the direction of the momentum matters, and it matters greatly. I want to add a few more things here because you're supposed to also remember the concept of impulse. There is, of course, angular impulse. So there's an analogy here. I do want to speak to you a little bit more critically about the direction of angular momentum.